In this video, we're going to go through an example problem that's in the book and go through it a little bit more thoroughly than they do in the book so that hopefully it's going to be more clear. Because this is the type of example that we're going to be continuing to do quite a bit in the course. So in this example, we have steam flowing through a nozzle. For reference, it's example 4.4 in your book. And steam is flowing in one side of this really poorly drawn nozzle. Here at state 1, it's flowing in 50 meters per second, 200 degrees Celsius, and 600 kilopascal. So it's flowing in, coming in at high pressure. It's leaving at low pressure, and we're exchanging some of the energy of pressure and heat, some of that thermal energy to velocity. So we're changing, converting, right, thermal to kinetic. That's our energy conversion process that's happening here. The control volume, well, there are really two control surfaces. So this is control surface 1, and then down here is control surface 2. So this is surface 1 where stuff is coming in, and this is surface 2 where stuff is leaving. I apologize for the poorly drawn perspective. But what's happening, okay, we can go through step by step and think about the things that are happening. So the first thing that we need to do is apply conservation of mass. So conservation of mass, here is the general equation here. In this specific case, we have mass coming in, the mass exiting m dot E. We're exiting at only one place, only here at control surface 2. And that must be equal to all of the stuff that's coming in. Well, we're only coming in at one place, m dot 1. So the mass balance is super easy. So because m dot 1 is equal to m dot 2, for the purposes of this problem, we'll just call it m dot. Okay, again, just for this particular problem, because we only have one inlet and one exit, so what comes in must go out. Okay, our next step after we apply a mass balance is to do the energy balance. So we're going to start with just writing the standard energy balance. So for a flow system like this, it's delta H equals delta E dot K plus delta E dot P equals Q minus W. So that's our standard energy balance, and now we're going to simplify. So we'll start with, we'll kind of go through all of these 5 terms in order. We'll start with work. So work is equal to 0 in this case because there is no shaft work. Right, there are, this is a piece of equipment, it's a nozzle. There are no moving parts that are adding work from somewhere external. There's no mechanical moving anything, it's just the nozzle. So there's no shaft work, right, no mechanical moving parts. That's why our work is 0. Our heat transfer is equal to 0 because, well, I guess this is an assumption. We're assuming that the system is insulated. It's not necessarily insulated. There could be heat coming in or heat leaving through the nozzle, but that's actually a relatively good assumption because if we look back and think about what's happening, apologize for that, but if we think about what's happening, we have this nozzle, we're coming in at 50 meters per second, and we're leaving at 600 meters per second. So I don't know, how big is this nozzle? Relatively small. So we're going to be blowing by there in much less than a second. So there's just not a lot of time for any heat transfer to take place. So that's why that's why this is a good assumption. A lot of times you'll see pieces of equipment or problems specifically saying the word insulated. That is a kind of a keyword that you should key in on and say, oh, that means that the heat transfer is 0. Another way to say that is that we call this a process where Q equals 0. We call this adiabatic. So this is a useful term that we're going to continue to use here in thermal, adiabatic. That means Q equals 0. All right. Now, the next one on our list is potential energy. So this is if we don't have any significant height change, then the change in potential energy is about 0. Right? So delta Z is basically equal to 0. It's a horizontal nozzle, so we wouldn't expect any significant height change. Okay, the next one, delta H. So we have steam / water flowing in and out. So we don't know what the properties are. So it's but we know that it's something that's flowing across the boundaries of our control volume in and out of CV. So that means that we can't automatically assume that that's equal to 0. We have to take it into account. There's stuff moving across, there's actual physical matter, so we have to look at that. The next is kinetic energy. Kinetic energy is not equal to 0 because velocity is changing. Right? We go back and look at our system. We're coming in here at 50 meters per second. We're leaving at 600 meters per second. We have this change in velocity. Okay, so we can get rid of 3 of these terms, right? We can get rid of work. We can get rid of W, Q, and potential energy, but we're left with these 2, delta H and delta EK. So our new energy balance becomes very simple. It becomes just delta H plus delta EK is equal to 0. So that's our new and simplified energy balance. Now we're going to write it out in detail, right? The delta just means out minus in. So this is going to be the sum of everything going out, or the exit, minus the sum of everything coming in. Right? This is the sum of all the enthalpy going out minus the sum of all the enthalpy flow into our control volume, as I have written down here. For this specific problem, the enthalpy that's coming out is the enthalpy of stream 2, and the enthalpy going in is the enthalpy of stream 1. Okay, those are flowing, so we'll put the little dots on them. And we can write that. We have, okay, let's look back at what we have. We have stuff flowing in at a specific mass flow rate, which we called m dot, right, over here. And it's flowing out at that same mass flow rate, again, m dot. And it's carrying with it some enthalpy here as it goes in at 1, and it's leaving with some enthalpy here at 2. So let's represent that. So the enthalpy that's leaving can be written as the mass flow rate times the specific enthalpy. And similarly, for the enthalpy coming in. Right, so we can write this, or delta H dot equals m dot H2 minus H1. Okay, and let's do the same thing, the same basic idea for kinetic energy. So the sum of all the kinetic energy exiting minus the sum of all the kinetic energy in the inlet stream. Right, kinetic energy is 1/2 mv squared. So we can write, right, all the stuff that's coming in is EK, or all the that's exiting is EK2 minus E dot K1. So out minus in, and that's 1/2 mv squared. So 1/2 m dot V2 squared minus 1/2 m dot V1 squared, where these bold letter V's, sorry, the bold V is velocity. We have a lot of V's in this class. We're going to use a bolded letter V for velocity. So we can rewrite that simply as delta E dot K equals 1/2 m dot, now V2 squared minus V1 squared. So we have now our two different equations. We have this one up here and this one down here that we can now put together. So if we put those two equations together, our energy balance is m dot H2 minus H1. So that was the enthalpy term plus 1/2 m dot V2 squared minus V, make it bold, V1 squared is equal to 0. So that is our energy balance now written out in terms of this specific problem. Right, so H is specific enthalpy, so we can look that up in tables, and this bolded V is velocity. So we've simplified it into the different things that we can put into tables. Our first step, which we'll write here in green, is divide both sides by m dot. So that just, right, this m dot cancels with this m dot. So our m dot sleeve, we're left with H2 minus H1 and 1/2 V2 squared minus V1 squared equals 0. We can do some basic rearranging and get now this equation for H2. H2 equals H1 plus 1/2 V1 squared minus V2 squared, right? The sign flipped because these guys got shuffled around all to the right-hand side of the equation. For H1, we know temperature and pressure for our inlet, so we can look up H1. So let's do that now. So we're looking up H1, it's going to be at 200 degrees C and 600 kilopascal. Okay, 200 C and 600 kilopascal. So let's go to our steam tables. I'm going to flip to steam tables right now. So let's first start looking at 200 degrees Celsius. So let's flip. We're going to start looking at the saturated water tables, and we're going to find 200 degrees Celsius. And we're going to see what pressure corresponds to that. So the pressure in our system was 600. What this is saying is the pressure would need to be 1553.8 for the system to be boiling. Because our pressure is less than that, that means we have a gas. If the pressure is more than that, we have a liquid. If it's less than this, we have a gas. So now we know we need to go to the superheated vapor tables. So we'll scroll down to, I believe this is superheated water vapor. So now we're looking at, 200 degrees and 600 kilopascal, and we're looking for H. So we have over here 200 degrees, so that's this column, and here is 600 kilopascal. So we're looking for H, which is this column here. So our number, if I'm looking at it right, is 2850.12, and the units are kilojoules per kilogram. This is 2850.12 kilojoules per kilogram. Right, that's from table B.1.3. So H2 we can now write is 2850.12 kilojoules per kilogram plus 1/2. Now V1 squared was 50 meters per second. So we have 50 meters per second squared minus 600 meters per second squared. So we're first going to look just at this part. Because that's the only part we have to do math on. So if we do that, okay, so V1 squared minus V2 squared is 50 meters per second squared minus 600 meters per second squared. We can do that math fairly easily, and we get this. But now we have goofy units. So this term has units of meters squared per second squared, and this term, H1, had units of kilojoules per kilogram. So let's take a little bit of a look at the units and make sure that these are actually related units that we can correspond to each other. Okay. So a joule, right? A joule is a unit of energy. A joule is 1 kilogram meters squared per second squared. A kilojoule is obviously 1,000 of those, so that's 1,000 kilogram meters squared per second squared. A kilojoule per kilogram, so we can just take this unit and divide it by kilogram, so that would be 1,000 meters squared per second squared. So yes, indeed, a kilojoule per kilogram is related to meters squared per second squared. So we could do our dimensional analysis. This would be 1 kilojoule per kilogram divided by 1,000 meters squared per second squared. So a meter squared per second squared is a joule per kilogram, so we have to divide by 1,000. If we go and do this math, our enthalpy is 2671.4 kilojoules per kilogram. So that's our exit enthalpy. Now, if we know our exiting pressure, P2, right? P2 was given in the problem. P2 was 150 kilopascal. And we know now from our energy balance, we know the exit enthalpy, 2671.4 kilojoules per kilogram. We can look now in our tables and figure out everything else about that state. So we'll look back at our table. So we have 2671.4 and 150. So we're going to go back to our steam tables. Again, we'll start. Now we know the pressure. So we're going to go to, use this. We're going to go to table B.1.4 because we're looking at pressure and we know pressure. So we know our pressure is 150 here. And we know our enthalpy. Okay, so here we have specific volume and internal energy. So let's go to the next section of this. Okay, so these three columns here are the ones that we're going to be looking at. And we want here a pressure of 150. So the enthalpy of a saturated liquid is 467. Our enthalpy is 2671, so we're higher than that. so we're not a compressed liquid. The enthalpy of a saturated vapor is 2693, right? So we are 2671.4. So our enthalpy is between these two values, between HF and HG. That means that we are a vapor liquid mixture. We're in between a saturated vapor and a saturated liquid. We're some mixture, like a mostly boiled vapor liquid mixture. So then it makes sense to find what the quality is of our vapor liquid mixture, right? What's the fraction which is gas? So we can find the quality, right? Because our H2 is less than Hg, as we saw, it's more than HF. We're a vapor liquid mixture. So we can find from those two values, from HF and HFG, now we can find that X, if you were to go and do the math, is about 0.99. So we're the water coming out of the nozzle is a vapor liquid mixture. It's at 150 kPa. We know the temperature. We flip back to our steam tables. The temperature is going to be the temperature of the vapor liquid mixture. So it's going to be 111.37. So 111.37 degrees C with a quality of 0.99. So by mass, it's going to be 99% vapor and 1% liquid. So this would tell us everything that we need to know about the water that's coming out. Hopefully that explains a little bit the thought process behind how you would go about these. Right, if we're thinking about what physically is happening, here physically we're changing thermal energy into kinetic energy in this nozzle. We see that by a change from enthalpy, which is the thermal energy of a moving fluid, into kinetic energy, which is obviously the mechanical energy. That's that velocity change. So we see as enthalpy goes down, right? Enthalpy decreases from 2850 to 2671. So as enthalpy goes down, kinetic energy goes up as we go from a velocity of 50 up to 600 meters per second. So that's how a nozzle is working. It's actually taking away some of the enthalpy of our fluid and converting that enthalpy into kinetic energy.